Hi everyone, my name is Dr. G. Naga Malleswari, Assistant Professor, Department of Mathematics from VNR JYOTHI Institute of Engineering and Technology, Hyderabad. In today's lecture, we discuss about the topic classification of singular points. Let us begin with the definition of zero of an analytic function. Zero of an analytic function. So first we see the definition of analytic function. What is an analytic function? The function that is differentiable. Analytic function is a function which is differentiable. The function that is differentiable at every point within its domain is called analytic function. But now we are discussing the zero of an analytic function. So zero of an analytic function is the function f of z is the value of z such that f of z is equal to 0. If suppose we are taking particularly a point A, at the point A is called zero of an analytic function f of z if f of A is equal to 0. See example for clear understanding of zero of an analytic function. Find the zeros of f of z is equal to z square plus 1 by 1 minus z square. We have to find out zeros of the function f of z is equal to z square plus 1 by 1 minus z square. What is given function? Given function f of z is equal to z square plus 1 by 1 minus z square. We have to find out zeros. The zeros of the function here f of z, zeros of the function f of z is given by f of z is equal to 0. What is f of z? F of z is equal to z square plus 1 by 1 minus z square. Z square plus 1 which can be written as z plus I into z minus I by 1 minus z square. Function f of z which is equal to 0. So how we can write this z square plus 1? Z square plus 1 which is equal to z plus I into z minus I. Again multiply these two. We get z square plus iz minus iz minus I square. See here, plus iz minus iz cancel. We get z square. I square is minus 1. Minus of minus 1 we get plus 1. Z square plus 1. So z square plus 1 which can be written as z plus I into z minus I by 1 minus z square is equal to 0. Then we get z plus I, z minus I is equal to 0. Therefore, z is equal to I and z is equal to minus I are simple zeros. So this is the procedure to find out zeros of a function. So how we can find out? First, given function f of z is equal to z square plus 1 by 1 minus z square. To find out the zeros of a function f of z, it is given by f of z is equal to 0. So z square plus 1 which can be written as z plus I into z minus I by 1 minus z square is equal to 0. So finally we get z is equal to I and z is equal to minus I are the simple zeros of the given function f of z is equal to z square plus 1 by 1 minus z square. Similarly, we can find out 0 of mth order. This is simple 0. So whatever the problem that we have to done is simple 0 problem. But how we can find out 0 of mth order? 0 of mth order. Here f of z is analytic function. F of z is analytic function and it can be expressed as f of z is equal to z minus a whole power m into phi of z, where phi of z is analytic and phi of a value which is not equal to 0, then z is equal to a is called 0 of mth order of the function f of z. So to find out the simple 0, we have to use f of z is equal to 0. Whereas to find out the 0 of mth order, we have to take f of z which is analytic function and f of z is equal to z minus a whole power m into phi of z. But here phi of z which is analytic function and phi of z at the point a which is not equal to 0, then z is equal to 0 is 0 of mth order of the function f of z. Next, we discuss the definition of singular point. What is singular point? The function f of z which is fails to be analytic is called singular point of a function f of z. So if the function, given function f of z which is not differentiable, so that means f of z is fails to be analytic, then that point we call it as a singular point of the function f of z. See the example. Consider function f of z is 1 by z minus 5. Here the function f of z is differentiable function, but at the point z is equal to 5, it is singular because at the point z is equal to 5, function f of z is fails to be analytic. Therefore, z is equal to 5 is singular point of the function f of z is equal to 1 by z minus 5. Next we discuss different types of singularities. First we discuss isolated singularity point. Isolated singularity. So what is an isolated singularity point? A point z is equal to z naught is said to be isolated singularity of the function f of z if it satisfies the following two conditions. What is the first condition? F of z is not analytic at z is equal to z naught. So z is equal to z naught means z is equal to at the point. So z naught here we are taking is the point. So first condition here is f of z is not analytic at z is equal to z naught. Then there exists a neighborhood z is equal to z naught containing no other singularities. If these two conditions are satisfied, then we say that the point is of having isolated singularity. See the graphical representation to clear understanding of isolated singularity and non-isolated singularity. See here the difference. In isolated singularity, isolated point is set of points where we can find the neighborhood around it. See here 3 points are there, z1, z2 and z3. So we can find the neighborhood z1, neighborhood point z2, z3 is there. Whereas in non-isolated singularity is a point where every neighborhood matters, how small it is, contains other points from the set. So this is the difference between the isolated singularity and non-isolated singularity. See example problem. f of z is equal to z by z square minus 1. We have to find out the isolated singularity for the given function f of z is equal to z by z square minus 1. How we can find out the isolated singularity? Function is given. First we have to note down the given function. Given f of z is equal to z by z square minus 1. This is given function. Z square, see denominator part, z square minus 1 which can be written as z plus 1 and z minus 1 because it is of the form a square minus b square form, so that it can be written as z plus 1 into z minus 1. Given function is analytic function. It is differentiable function. Given function is analytic function except at the points. So which points it is not differentiable? Z is equal to minus 1 and z is equal to plus 1. So given function is analytic function except at the point z is equal to 1 and z is equal to minus 1. Therefore, z is equal to 1 comma minus 1 are two isolated singular points. So here for the given function we have two isolated singular points. One is z is equal to 1 and another one is z is minus 1. See another example. Here also we have to find out the isolated singularity for the given function f of z is equal to e power z by z square plus 1. Given function. First we have to note down the given function. F of z is equal to e power z by z square plus 1. So in denominator z square plus 1 is there. Z square plus 1 which can be written as z square plus 1 is equal to 0. We get z square is equal to minus 1. Then z is equal to plus or minus I. Therefore, z is equal to plus I and z is equal to minus I are two isolated singular points. Singular points of the given function f of z is equal to e power z by z square plus 1. Next, see important note here. If z is equal to z naught is an isolated singular point of the function f of z, then the singularity is called, so that singularity we call it as a removable singularity, or it is a pole, or it is an isolated singularity. According as the Lorentz series about the point z is equal to z naught of the function f of z. So function f of z having no negative powers, a finite number of negative powers, or it is of having an infinite number of negative powers. See what is Lorentz series expansion. See first Lorentz series expansion. See what is Lorentz series expansion. Let C1 and C2 are two circles. C1 and C2 are two circles. Let us draw the two circles C1 and C2. One circle is C1 and note down another circle, this is C2. C1 and C2 are two circles and Z is any point in these two circles. Z is a point two circles which is of having radius, and it is denoted by z minus a, which is equal to r1, and z minus a is equal to r2. So two different circles which is of having radius r1 and r2. But here radius of r2 is less than r1, and z is any point on C1 and C2. Then the Lorentz series expansion f of z is given by f of z is equal to summation n is equal to 0 to infinity an z minus z naught. At z naught we have to take the point a also. Z minus z naught whole power n plus summation n is equal to 1 to infinity bn by z minus z naught whole power n, where an is equal to 1 by 2 pi I closed integral over c f of z by z minus a whole power n plus 1 into dz, and bn is equal to 1 by 2 pi I closed integral over c f of z by z minus a whole power minus n plus 1 into dz, where the integrals taken around the circle C1 and C2 in anti-clockwise direction. And see here, this is analytic part, and here it is principal part. Summation n is equal to 0 to infinity an z minus z naught whole power n is analytic part, and summation n is equal to 1 to infinity bn by z minus z naught whole power n is principal part. So this is the expansion of Lorentz series. So according as Lorentz series, about the point z is equal to a, or about the point z is equal to z naught of the function f of z, so it is of having no negative powers, finite number of negative powers, or it is of having an infinite number of negative powers. Next, we discuss the definition of removable singularity. If the principal part of, so principal part means summation n is equal to 1 to infinity bn by z minus z naught whole power n. So this is the principal part. If the principal part of f of z contains no terms, so no terms means that is bn is equal to 0 for all the values of n, then the singularity z is equal to a is called removable singularity of f of z. If bn is equal to 0, then we get the function f of z is equal to summation n is equal to 0 to infinity an z minus a whole power n. Or we can use another definition for removable singularity. A singular point z is equal to z naught is called removable singularity of the function f of z if limit z tends to z naught f of z exists finitely. So this is also the definition that we are using for removable singularity, or the principal part of f of z which contains no terms, that is bn is equal to 0 for all the values of n. Next, see the example problem. Function is given f of z is equal to sin z by z. First we have to note down the given function. Given function f of z is equal to sin z by z. Sin z by z is equal to 1 by z into, we have to note down the expansion of sin z. What is the expansion of sin z? Z minus z cube by 3 factorial plus z power 5 by 5 factorial minus and so on. So now we have to note down it as f of z is equal to 1 by z into expansion of sin z, z minus z cube by 3 factorial plus z power 5 by 5 factorial minus and so on. Multiply the whole expansion with 1 by z. We get 1 minus z square by 3 factorial plus z power 4 by 5 factorial minus and so on. Here there is no negative powers. There is no negative powers of z. Therefore, z is equal to 0. Z is equal to 0 is a removable singularity. So this is the procedure to find out the removable singularity. So what we are doing, first we have to note down the given function, and next step is we have to write the expansion of sin z. Sin z expansion is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus and so on. Next, multiply it with 1 by z. We get function f of z as 1 minus z square by 3 factorial plus z power 4 by 5 factorial and so on. Here no negative powers are existing of z. So that means no negative powers of z are there. Therefore, z is equal to 0 is a removable singularity for the given function f of z is equal to sin z by z. Next, we discuss the definition of a pole. So what is a pole? If we can find the positive integer n such that limit z tends to z naught, z minus z naught whole power n into f of z value which is not equal to 0, then z at the point is called pole of order n for the function f of z. Or simply we can note down, if limit z tends to z naught, f of z is equal to infinity, then z is equal to z naught is pole of the function f of z. Simple pole. So what is a simple pole? Simple pole means it is a pole of order 1. Pole of order 1 we call it as a simple pole. See the example problem. If f of z is equal to z square by z minus 1 z plus 2 whole square, then given function f of z is z square by z minus 1 z plus 2 whole square. Take the denominator part, z minus 1 is there and z plus 2 whole square is there. So from this what we get? Z is equal to 1. And from this we get z is equal to minus 2 comma minus 2. So z is equal to 1 is pole of order 1, so that it is called a simple pole. And z is equal to minus 2. So z plus 2 whole square is there here. We get z is minus 2 comma minus 2. Z is equal to minus 2 is pole of order 2. Next definition, essential singularity. If the principal part of the function f of z contains an infinite number of terms. So principal part means here it is denoted by Bn, and that principal part of f of z which contains an infinite number of terms. That is, so this is the principal part. In Lorentz series expansion, summation n is equal to 1 to infinity Bn by z minus a whole power n. Principal part of the function contains an infinite number of terms. Then the point z is equal to z naught is called essential singularity of f of z. See example problem. Given function is f of z is equal to e power 1 by z. We have to find out the essential singularity for the given function f of z. So how we can find out the essential singularity? Function is given. First we have to note down that f of z is equal to e power 1 by z. So what is the expansion of e power x? E power x expansion is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. But here in place of x, 1 by z is given. E power 1 by z is 1 plus 1 by z plus 1 by z square into 1 by 2 factorial plus 1 by z cube into 1 by 3 factorial plus and so on. So principal part of f of z which contains an infinite number of terms. When the function becomes infinity at z is equal to 0. Therefore, z is equal to 0 is an essential singularity. So function contains an infinite number of terms means we have to take the point of z where we get the infinite value. But here at z is equal to 0, we get infinity. Therefore, z is equal to 0 is an essential singularity. Next, see the example problem. What is the nature of singularity z is equal to 0 of the function f of z is equal to sin z minus z by z cube? First, note down the given function. Given f of z is equal to sin z minus z by z cube. We have to find out the nature of singularity z is equal to 0. Here, to find out the nature of singularity of the function, better we have to apply L'Hospital rule. Apply L'Hospital rule. Limit z tends to 0. Apply L'Hospital rule for the function sin z minus z by z cube. So differentiation of sin z is cos z minus 1 by 3 z square. Again apply L'Hospital rule. Limit z tends to 0. Cos z differentiation is minus sin z by 6z. Again we are applying L'Hospital rule. Limit z tends to 0 minus cos z by 6. Then apply the limit. Limit z tends to 0. So if you are applying the limit z is equal to 0, we get minus 1 by 6. Here limit is existing because we get the limit value which is minus 1 by 6. Limit is existing and is finite value. Therefore, z is equal to 0 is given. Z is equal to 0 is a removable singularity. Right? Next, see another example. Classify the singularity of f of z is equal to tan z by z. So we have to identify which type of singularity is existing for the given function f of z is equal to tan z by z. First note down the given function. Given f of z is equal to tan z by z. Now f of z is equal to 1 by z into, we have to note down the expansion of tan z. So what is the expansion of tan z? Z plus z cube by 3 plus 2z power 5 by 15 plus and so on. So multiply this whole expansion with 1 by z. We get 1 plus z square by 3 plus 2z power 4 by 15 and so on. Limit z tends to 0. Function is tan z by z is equal to 1, which is not equal to 0. Therefore, z is equal to 0 is a removable singularity. Try the following these two examples. First one is identify the type of singularity. Here we have to find out which type of singularity is existing. Type of singularity of the function f of z is equal to sine of 1 by 1 minus z. And second question, find the singular point of the function f of z is equal to sine z into 1 by z minus a. Here also we have to find out the nature of the singularity. Try these two examples. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.